Question 3. The outer layers of some golf balls are made from a polymer called polyisoprene. The isoprene monomer is non-cyclic, in other words, it's a chain, so it's not joined in some kind of circular shape. It is branched, and it's a hydrocarbon, so it contains hydrogen and carbon only, so we know it only contains those two elements. It contains 88.2% carbon by mass, so by subtraction we can work out the percentage of hydrogen in there. So let's have a look how we go through this. So percentage of mass carbon is 88.2, hydrogen must be 100, take away 88.2, which is 11.8. You divide to work out the ratio, the ratio of the number of atoms in the molecular or the empirical formula. You divide by the mass number of each of them. The mass number of carbon is 12, so you divide by 12. The mass number of hydrogen is 1, divide by 1. So there's 7.35 to 11.8. I've got to get these into whole numbers. So I divide by the smaller of the two, so I divide by 7.35, and I divide this one by 7.35, so you find the small number of the two. You divide both of these numbers by the smaller number, and then it comes out as a ratio that's closer then to whole numbers, 1 to 1.61. Now I've got to multiply by a number to get whole numbers, so if I multiply this by 5, it gets very, very close to 8. So I multiply both by 5 to 8. So the empirical formula, which is the molecular formula, it says the empirical formula and the molecular formula are the same, so C5H8. Now how do I then deduce the structure? Well, I know it's branched. I know it's got 5 carbons, and it can't have single bonds, otherwise CnH2n plus 2 would be C5H12. If it had one double bond, it would be C5H10, CnH2n. So it's going to have 2 double bonds, because I've got fewer hydrogens than 10. So one double bond would be C5H10, CnH2n for an alkene. So I've got an extra double bond in there, which will lower the number of hydrogen atoms still. So I've got to have 5 carbons, 2 double bonds. It's a branch chain, so we'll try 4. 1, 2, 3, 4. You can do it. It says do a structure, so you could do the displayed formula instead, or you could do the structural formula as I've done here. 1, 2, 3, 4 with a branch, and I've put 2 double bonds in. So the double bonds are at carbon number 1 and carbon number 3 with a methyl group as well. And that's the only structure that you can have. You could try others, but you'll find that's the only structure that works out with a branch chain, 5 carbons and 2 double bonds. There's no other way to draw it. The insides of some golf balls are made from a mixture of 3 other polymers. The repeating unit for one of these polymers is shown below. So this is how it is as a polymer, with these chains going along. So this will form the sort of backbone, the middle part of the polymer, with carbon bonds going outside, and then each of these units will then repeat and repeat and repeat, and we've got this group here with 2 carbons and a double bond as a branch off the chain. So draw the skeletal form of the monomer. So before these bonds, these single bonds, have bonded either side, left and right, to make the polymer, it's been this monomer here with a double bond. So you take the 2 single bonds that are going left and right to form the sort of chain, the middle chain, the skeleton of the backbone of the polymer, and you make this here into a double bond. So this double bond is broken and a bond has gone left and right to make the long polymer chain. So that's all you have to do. The skeletal formula of this, then, you remove all the H's and you put the C's as dots and or corners, and it looks like this then. So I've got a double bond, and then I've got a single bond, and I've got a double bond, double, single, double, and all the hydrogens are then not shown. UPAC name of this, it's a diene, 2 enes, 2 double bonds. It's butadiene, and they're at carbons number 1 and carbon number 3. So it's but-1,3-diene. That's its UPAC name, that's its real name. The second polymer in the mixture has a repeating unit structure shown below. A third polymer is a stereoisomer. So a stereoisomer has the same structural formula but different arrangement of atoms in space. And you can see here, if I go to the left of the double bond, if I go to the left of the double bond and I trace it, so if I use Carningol prelog, then the top group, the CH2, takes priority in both cases because the carbon bonded to the left-hand carbon has got an atomic number of 6, whereas the hydrogen below has only got an atomic number of 1, and the same on the right-hand side. So that is Z, that's the Z isomer. So now what I've got to draw is the E isomer, where they are opposite each other. Give a reason why this type of stereoisomerism arises is because there's no free rotation around the double bond. Golf balls are recovered from lakes and ponds, again after being in water several years. Explain why these golf balls do not biodegrade, because you'd have to break the very strong carbon to carbon bonds. So carbon to carbon bonds are very strong.